Hello there, and welcome to the Sleepy Science Channel. Tonight we embark on a journey to one of Earth's most mesmerizing natural wonders. We'll venture to the far north, to lands where the sky itself comes alive with light and color. We'll explore the Aurora Borealis, the northern lights, a phenomenon that has captivated humanity for millennia, inspiring myths, driving explorers, and reminding us of our profound connection to the sun and the planet we call home. The northern lights are both ordinary and extraordinary. They happen regularly in certain parts of the world, yet they never cease to amaze those who witness them. They are predictable in their patterns, yet unique in every appearance. They are a dance of physics and magnetism, of solar wind and atmospheric gases, of light scattered across the darkness. If you have ever dreamed of witnessing them, or if you simply wish to understand the quiet magic that unfolds in the polar night, settle in and let the story of the aurora carry you toward rest. The ancient mystery, long before scientists understood the mechanisms behind the northern lights, humans gazed upward in wonder and fear. The indigenous peoples of the Arctic, the Inuit, the Sami, the various nations of the northern latitudes developed their own stories to explain the shimmering curtains of light that sometimes filled their night skies. These were not merely explanations, but sacred narratives woven into their cultures, their survival strategies, and their deepest spiritual beliefs. In the darkness of the Arctic winter, when the sun vanishes for weeks or months, the auroras became companions. The Inuit peoples saw in them the spirits of their ancestors, engaged in a celestial game of ball, kicking the head of a walrus back and forth across the heavens. This wasn't simply a poetic fancy, it was a way of understanding the aurora that integrated it into their worldview, making sense of the strange and beautiful phenomenon. The lights danced, as if playing, and in this observation lay a kernel of truth. The aurora is indeed a kind of cosmic dance, though the partners are particles and fields rather than spirits. Other northern cultures developed their own interpretations. The Sami people, reindeer herders of Scandinavia, warned against the aurora and advised people not to whistle or wave at the lights, lest they attract dangerous supernatural attention. Some sources suggest the aurora might warn of death or misfortune. Yet even within these cautionary tales, there was respect and acknowledgement that something powerful and otherworldly was taking place above them. The Norse peoples, in their great sagas and mythologies, sometimes interpreted the lights as fires or reflections from the armor and weapons of the Valkyries, the female warriors who chose the slain on battlefields. The lights became battle lights, cosmic struggles playing out in the sky. This interpretation reflected their culture's fascination with warfare and the supernatural, while simultaneously capturing something true about the aurora. It is indeed a kind of violence, a collision of energies from the sun meeting Earth's magnetic shield. As we lie here and contemplate these ancient understandings, we might find something profound in them. Before we had spectrographs and satellites, before we could measure solar wind speeds and ion temperatures, humans looked upward and tried to make meaning of what they saw. They created stories that held cultural significance, that connected the sky to their lives, that made the vast and incomprehensible, at least somewhat graspable. In a way, we still do the same. Today we simply use different tools and a different language. The birth of scientific understanding. The northern lights remained a mystery to the broader scientific community for centuries after ancient peoples had woven them into their stories. During the Middle Ages and Renaissance in Europe, the lights were often interpreted through a religious or astrological lens. They were omens, portents, signs from heaven. In 1621, a Swedish scientist named Anders Celsius, yes, the man whose name is now attached to a temperature scale, began conducting more systematic observations of the aurora in Uppsala, Sweden. But even Celsius, with his scientific training, struggled to explain the phenomenon. The aurora remained largely mysterious to formal science. Throughout the 1700s and 1800s, as the scientific revolution progressed, more researchers turned their attention northward. Scientists traveled to the Arctic and subarctic regions specifically to study the lights. They made detailed observations, trying to understand what conditions produced the aurora and what physical mechanisms might explain it. They noted that the aurora seemed to correlate with disturbances in Earth's magnetic field. They observed that the lights had colors, greens, reds, purples, blues, and tried to understand what caused these variations. One of the great breakthroughs came with the understanding of electricity and magnetism in the 19th century. Scientists began to suspect that the aurora was somehow related to electrical and magnetic phenomena. If Earth itself had a magnetic field, and if the Sun emitted some kind of charged particles, then perhaps the interaction between these two things created the aurora. But this was still theoretical. Direct proof remained elusive. The real transformation came in the 20th century, with the advent of the space age. When scientists could launch satellites into orbit and measure the solar wind directly, when they could study the magnetosphere from above, suddenly the pieces fell into place. The aurora wasn't magic or mysticism or divine intervention. It was physics, elegant, beautiful, understandable physics. The sun, our star's hidden power. To truly understand the aurora, we must begin with the sun. Our sun is not a simple, stable ball of burning gas, as it might appear from Earth. It is a dynamic, turbulent giant, a roiling furnace of nuclear reactions and magnetic fields. At the sun's core, hydrogen is constantly fusing into helium under conditions of such extreme temperature and pressure that it's almost impossible to comprehend. This process releases the energy that powers all life on Earth, but it also creates something else, a constant stream of charged particles. The sun does not merely emit light and heat. It also emits what scientists call the solar wind, a continuous flow of charged particles, primarily electrons and protons, streaming outward from the sun in all directions. This solar wind is always there, always flowing, carrying with it the sun's magnetic field. When we look at the sun on a quiet day, this wind is relatively gentle, but the sun is not always quiet. On the surface of the sun, phenomena occur that seem almost violent on their scale. Sunspots appear and disappear. These are regions of intense magnetic activity. Solar flares, sudden, intense eruptions of energy on the sun's surface, occur regularly, sending bursts of radiation across the solar system. Even more dramatic are coronal mass ejections, or CMEs, in which enormous bubbles of magnetized gas are hurled outward from the sun's atmosphere, the corona. These events can hurl billions of tons of material into space at speeds of millions of kilometers per hour. When these events occur, the solar wind intensifies dramatically. It's no longer a gentle breeze of particles, but a gust, a storm, a torrent. This is what the sun sends toward Earth. Most of the time, Earth is spared the worst of this activity, because our planet has a protective shield, the magnetosphere, Earth's magnetic armor. Imagine Earth surrounded by an invisible shield. This shield is our magnetic field, generated by the swirling of molten iron in Earth's core. The magnetosphere extends far into space, creating a protective bubble around our planet. It's this shield that protects us from the worst of the solar wind's effects. The magnetic field is strongest near Earth's surface and weakens with distance, but it extends tens of thousands of kilometers outward. The magnetosphere is shaped by the pressure of the solar wind. On the side of Earth facing the sun, the solar wind compresses the magnetosphere, pushing it closer to the planet. On the opposite side, the magnetosphere is stretched out, forming a long tail that extends far into space, sometimes as far as the moon and beyond. This magnetosphere is not rigid or static. It's dynamic, constantly flexing and changing in response to variations in the solar wind. When the solar wind is gentle, the magnetosphere maintains a relatively stable structure. But when a coronal mass ejection hits, or when solar activity increases dramatically, the magnetosphere can become distorted, compressed, and unstable. Crucially, the magnetosphere has a particularly interesting shape in the polar regions. The magnetic field lines converge toward the north and south magnetic poles, creating a funnel-like structure. These field lines are not solid things. They are regions of space where the magnetic force is aligned in a particular direction, but they guide the movement of charged particles with remarkable efficiency. The collision of worlds. And here is where the aurora begins to take shape. When charged particles from the solar wind encounter Earth's magnetic field, they are not simply stopped or deflected uniformly. The particles follow the magnetic field lines. Those that are guided toward the polar regions are funneled downward, toward the upper atmosphere. The solar wind particles, mostly protons and electrons, are invisible. They carry energy, but we cannot see them. When they collide with the upper atmosphere, approximately 100 to 300 kilometers above the Earth's surface, something remarkable happens. The particles from space collide with the atoms and molecules of Earth's atmosphere, primarily oxygen and nitrogen, transferring energy to them. These atmospheric gases, having absorbed this energy, become excited. In physics, excited means that electrons within the atoms have jumped to higher energy levels. But excited atoms want to return to their normal state. To do so, they must release the energy they've absorbed. They release this energy as light as photons of light. This is the aurora. The color of the aurora depends on which atmospheric gas is involved and at what altitude the collision occurs. Oxygen atoms, when excited, typically emit light in two primary wavelengths: a green-yellow light, around 558 nanometers, and a deep red light, around 630 nanometers. It is the green-yellow line that dominates most auroral displays, creating that characteristic bright green glow that most people associate with the northern lights. Nitrogen, when excited, produces blues and reds. At higher altitudes, where oxygen is more abundant, the lights tend to be green. At lower altitudes, or when there is significant nitrogen involvement, blues and purples may appear. Very intense displays can produce all these colors at once, creating a spectacular rainbow of light across the polar sky. The aurora's favorite latitude. If you were to draw a circle around Earth, around 65 degrees north latitude, you would trace the auroral oval. This oval is the preferred location for aurora activity. It passes through parts of Alaska, Canada, Scandinavia, and Siberia. The auroral oval is most prominent during geomagnetic storms, periods of intense aurora activity caused by strong solar wind disturbances, but some form of aurora often occurs within this zone. In places like northern Canada, Alaska, Scandinavia, and Iceland, the aurora can appear many nights per year during the clear, dark season. Some locations experience aurora displays several times per week during winter months. The most remote stations and highest latitude settlements might see aurora on clear nights throughout much of the winter. In Fairbanks, Alaska, for instance, the aurora appears on roughly 240 nights per year, though many of these displays might be subtle or occur when the sky is still twilight blue rather than fully dark. The reason the aurora concentrates in this oval relates to the geometry of Earth's magnetic field. The magnetic field lines converge toward the magnetic poles, which don't coincide exactly with the geographic poles. The magnetosphere's interaction with the solar wind creates instabilities primarily in this auroral zone. It's as if the magnetosphere has a seam, and the auroral oval marks that seam. Those who live within the auroral oval experience aurora as a natural part of their environment, much as people in temperate latitudes experience rain or snow. Some residents of the far north have grown up watching the aurora appear regularly on winter nights, stepping outside in the cold darkness almost casually to glimpse the lights before returning to their warm homes. Yet even for those accustomed to seeing the aurora, it rarely becomes boring. Each display is unique, never quite the same as any previous night. Those living farther south rarely see the aurora, unless geomagnetic storms are particularly intense, pushing the auroral oval farther toward the equator. During the most extreme geomagnetic storms, which occur roughly once per decade or so, the aurora might be visible from much farther south. In 1989, a massive geomagnetic storm made the aurora visible from Cuba. In other extreme storms, the aurora has been seen from the southern United States, Europe, and even farther equatorward. These rare events remind those of us living in more temperate latitudes that the aurora is always there, always potentially visible, if only the conditions align. The breadth of activity. The aurora is not constant. On a quiet night in the north, there might be a faint glow along the northern horizon, a subtle luminescence that barely rises above the stars. This is a quiet auroral glow produced by low-level activity in the solar wind and magnetosphere. But then, conditions change. Sometimes, over the course of an hour or so, the aurora awakens. A faint arc that was barely visible suddenly brightens. The arc begins to ripple and dance. Curtains form sweeping, folding sheets of light that move across the sky. The green becomes more vivid, more intense. The aurora seems almost alive, breathing and pulsing with energy. This is an auroral substorm, a period of intensified activity lasting perhaps 30 minutes to an hour. During a substorm, the amount of energy being deposited into the atmosphere is staggering. Particles that were previously just slowly drifting along magnetic field lines suddenly accelerate dramatically. Bright auroral curtains form where the energy deposition is most intense. The aurora during a substorm might be bright enough to illuminate the snow-covered ground, to cast shadows, to be easily visible, even from towns with some light pollution. The physical mechanism behind substorms is not yet completely understood, even by the scientists who study auroras professionally. What is known is that the magnetosphere accumulates energy from the solar wind over time. This energy is stored in the stretched magnetic field lines on the night side of the magnetosphere. Then, suddenly, this stored energy is released catastrophically. Particles accelerate. Magnetic field lines snap and reconnect in different configurations. Enormous amounts of energy flow downward into the atmosphere, causing the aurora to brighten dramatically. To those watching from the ground, a substorm is usually the most spectacular part of an auroral display. The aurora transitions from a gentle background glow to something more active and dramatic. Waves propagate along auroral curtains. Rays shoot upward from the horizon toward the zenith. New arcs form in the east or west and expand across the sky. For someone who has come north specifically to see the aurora, a substorm is often the goal, the moment when the lights truly come alive. The colors of the night. As we rest here and imagine the aurora dancing above us, let's contemplate the colors more carefully. The most common auroral color is a soft, green-yellow light. This comes primarily from oxygen atoms at altitudes of 100 to 150 kilometers. The wavelength is so distinctive, 558 nanometers, that it's sometimes called the auroral green line. It's a color that's difficult to describe accurately to someone who hasn't seen it in person. It's not quite like any terrestrial green. It seems almost ethereal, glowing with its own internal light. This green is often the brightest part of the aurora. It's the color that dominates photographs and descriptions. Yet, it's not the only color. At higher altitudes, above 300 kilometers, oxygen atoms excited by particle collisions emit a deep red light at 630 nanometers. This red is much fainter than the green under most circumstances, about 100 times fainter. But during very intense displays, the red becomes visible, often appearing as a red glow at the top of auroral curtains or forming a reddish corona overhead. The reds and purples often appear together with the greens, usually during the most intense auroral displays. The transition between colors can create stunning visual effects. An auroral curtain might have a green lower edge, the more intense region, with a reddish glow above it, creating a rainbow-like effect. Purple colors sometimes appear as well, usually a mix of the red and blue colors produced by nitrogen. The blues come from nitrogen and typically appear at somewhat lower altitudes than the red oxygen line, between 100 and 300 kilometers. Nitrogen produces both blue and red colors, depending on the energy of the exciting particles, but the blue is often fainter than the green and red, visible primarily during very intense displays or near the bottom of auroral curtains where nitrogen is more abundant. One of the fascinating aspects of the aurora is how the colors reveal information about what's happening physically. The altitude of a particular auroral feature tells us about the energy of the particles causing it. The relative brightness of different colors tells us about the composition of the atmosphere at different heights. Scientists studying the aurora can actually learn about atmospheric properties by analyzing the colors of the light. The aurora, in effect, is writing a scientific data stream across the sky. The dance of light and magnetism. The aurora is not random. While each auroral display is unique, there are patterns. These patterns reflect the underlying physics of how charged particles interact with magnetic fields. One of the most common auroral patterns is the auroral arc. An arc is a bright band of light that stretches across the sky, usually running roughly east-west. The arc might be sharp and well-defined, or diffuse and fuzzy. It might remain relatively stable for minutes or hours, or it might brighten and fade repeatedly. An arc is a region where many particles are being accelerated to energies sufficient to produce visible light, and where the particle precipitation is concentrated in a narrow band. As particles accelerate and the auroral activity intensifies, arcs often break up. Instead of a simple smooth arc, the arc develops structure. Bright, narrow rays form pillars of light that shoot upward from the main arc toward the zenith. These rays are sometimes called auroral curtains or auroral streamers. A particularly active display might have dozens of rays, each tens of kilometers wide, extending hundreds of kilometers into the sky. To an observer on the ground, these rays appear to reach toward the zenith directly overhead, though in reality they usually slope due to the orientation of the magnetic field. The rays don't remain static. They shimmer and ripple. They brighten and fade. Sometimes they pulse, growing brighter and dimmer in a regular rhythm. Sometimes they twist into spirals or helical shapes. To watch an auroral curtain is to watch something almost alive, something that seems to breathe and dance according to rules we don't fully understand. The movements are usually too slow to see in real time if you blink or look away, but slow-motion video reveals the subtle dance that's always happening. Another common pattern is the auroral corona. When a particularly bright display reaches its peak, and when you're standing beneath the aurora, it can form what looks like a crown or halo directly overhead the corona. The rays converge toward a point near the zenith, creating a three-dimensional effect that's extraordinarily dramatic. To stand beneath an auroral corona is to feel small, to feel connected to something vast and powerful. The aurora that seems to be above and around you simultaneously, coming down from all directions at once. Between displays, during quieter periods, the aurora might fade to a mere glow, what's called the auroral glow or quietly glowing auroras. This is a diffuse, often quite faint light, with little structure. It's produced by low-level particle precipitation, not intense enough to create bright arcs or curtains. A glow aurora might be so faint that it's not visible at all from locations with significant light pollution, but from a truly dark location, it provides a subtle background to the night sky. The seasonal and solar rhythm. The aurora varies on multiple timescales. There are variations within a single night as magnetic conditions change. There are variations between nights as solar activity waxes and wanes. And there are variations on longer timescales, tied to both the solar cycle and Earth's orbital position. The aurora is most visible during the dark season. In locations close to the Arctic Circle, this means the long polar night of winter, when the sun never rises. In locations farther south, it simply means the clear dark nights of fall, winter, and early spring. In summer, when the sky remains twilight blue throughout the night or the sun doesn't set, the aurora is still happening, but it's simply not visible because the sky is already lit. There's also a solar cycle that affects overall aurora activity. Every approximately 11 years, the sun goes through a cycle of activity. Near the solar maximum, sunspots are numerous. Solar flares and coronal mass ejections occur frequently, and aurora activity is generally higher. During solar minimum, activity decreases. The sun is quieter, sunspots are rare, and aurora displays are generally less frequent and less intense, though they still occur. We are currently in a period of increasing solar activity, heading toward a solar maximum around 2025. There's also an intriguing longer-term variation called the geomagnetic disturbance time, or K-index, as scientists call it. Geomagnetic storms follow a daily pattern. They tend to be most intense in the hours after midnight and before dawn. This is related to how the solar wind interacts with the magnetosphere throughout the day. In the evening hours, conditions are often building, but not yet at their peak. Around midnight to 2 a.m. local time, intense substorms are most likely. This is one reason that many aurora hunters in the north, if they wake for work or can't sleep easily, find that a quick look outside in the middle of the night often rewards them with aurora activity. Watching from the far north, in places like Tromsø, Norway, Yellowknife, Canada, Fairbanks, Alaska, or Kiruna, Sweden, people live with the aurora. They build their lives around the long darkness. Tourists come from around the world to see the lights. Locals who have grown up with them often say they never quite lose their sense of wonder, even after seeing the aurora hundreds or thousands of times. Tromsø sits at 69 degrees north latitude, deep within the auroral oval. From roughly September through March, the sky is dark enough for the aurora to be visible, and the statistical likelihood of seeing it on any given clear night is high. Tourists book hotels specifically to have windows facing north, where the aurora is most likely to appear. Local guides lead groups out into the Arctic night to hunt for the lights. Many of these tours wait until late in the evening or even into the early morning hours, as this is when auroral activity is statistically most likely. Yellowknife, in the Northwest Territories of Canada, is another aurora hotspot. At 62 degrees north latitude, it's slightly farther south than Tromsø, but it's still well within the auroral oval. The city has become something of an aurora watching destination. Aurora cabins dot the landscape around the city. Small heated structures designed so that tourists can watch the lights from inside while remaining warm. The view through a large window at a comfortable temperature, with hot drinks and comfortable seating, has become the standard way many people experience the aurora. Fairbanks, at about 65 degrees north, experiences aurora displays with even greater frequency than slightly lower latitude locations. The University of Alaska Fairbanks operates one of the world's premier geophysical institutes, where scientists study the aurora and space weather. From Fairbanks, the aurora is close enough to be a normal part of winter life for residents. A resident might glance outside and see the lights dancing, much as someone in a southern city might notice rain in the afternoon. Yet, even in these places, the aurora remains special. A particularly bright display, a display with unusual colors, a display of unusual duration. These are things that people talk about, that locals point out to tourists, that inspire photographers to spend hours in the cold, waiting for the perfect shot. The aurora never becomes mundane, even in places where it appears regularly. The aurora's connection to Earth's history. The aurora we see today is the same aurora that humans have seen for millions of years, as long as Earth has possessed a magnetic field. But the aurora's appearance has changed throughout Earth's history, and understanding this history helps us appreciate what we see today. Earth's magnetic field has not remained constant. In fact, roughly every 200,000 to 300,000 years, on average, Earth's magnetic field reverses. The north and south magnetic poles trade places. During these reversals, which can take between 1,000 and 10,000 years to complete, the field becomes very weak. During such times, the aurora would have been far more dramatic and visible from much farther south than it is today. The auroral oval would have expanded dramatically, and the aurora might have been a common sight at the equator. More recently, about 11,700 years ago, during what's called the Younger Dryas period, there was a prolonged return to Ice Age-like conditions. Some scientists have theorized that a comet or asteroid impact might have triggered this reversal in climate. If such an impact occurred, it might have been visible from Earth's surface as a brilliant display in the sky, perhaps visible in the daytime as well as night. Some have speculated that ancient astronomical events described in mythologies around the world might have been references to particularly bright auroras during periods of extreme solar activity or an especially weak magnetic field. While this remains speculative, it's clear that the aurora has always been a part of the Earth system. The global auroral dance. While the northern lights capture most of the attention and have been extensively studied, there is a counterpart in the southern hemisphere. The aurora australis, or southern lights, is essentially the same phenomenon occurring at southern latitudes. It's most commonly seen from the Antarctic and the far south of Australia, New Zealand, and southern Chile and Argentina. The auroral oval at the south magnetic pole creates the same beautiful displays as the north, just occurring in different locations. The northern and southern auroras are mirror images in many ways, but they're not perfectly synchronized. They occur simultaneously, driven by the same solar wind disturbances, but subtle differences in the geometry of the magnetosphere and the local conditions in each hemisphere can cause slight variations in how the auroras appear and behave. In recent years, with the advent of satellite technology and the accumulation of decades of observations, scientists have begun to understand the northern and southern auroras, not as isolated phenomena, but as part of a global system. Energy from the solar wind flows into the magnetosphere, is concentrated in the auroral oval regions at both poles, and is dissipated into the atmosphere in the form of particle precipitation. This creates the aurora not just a local phenomenon, but a global one, playing out simultaneously in both the Arctic and the Antarctic. The physics of acceleration. One of the great mysteries that aurora researchers continue to work on is, how are the particles accelerated to such high energies? In the upper atmosphere, where the aurora occurs, the ambient temperature is very cold, only a few hundred degrees Kelvin. Yet the particles causing the aurora have energies equivalent to much hotter temperatures, thousands of degrees. Something is accelerating them to these energies. Scientists have identified several possible mechanisms. One is acceleration along magnetic field lines in regions where the magnetic field is highly curved or where there are electrical fields. Another is acceleration during the reconnection of magnetic field lines. When the lines snap and reconnect in a lower energy configuration, they release energy that can go into accelerating particles. A third involves wave-particle interactions, where plasma waves in the magnetosphere can impart energy to particles. The relative importance of these different mechanisms is still being debated and researched. Modern satellites with sensitive particle detectors continue to gather data that help us understand how this acceleration occurs. It's a reminder that despite centuries of aurora observations and decades of space-age research, mysteries remain. The aurora is still teaching us about the fundamental physics of how charged particles behave in electromagnetic fields. The colors of deep time. As we rest and contemplate the aurora, we might think about how this phenomenon connects us to deep time. The aurora that we see today has been occurring for as long as Earth has had a magnetic field and an atmosphere, which is to say, for roughly 4.5 billion years. Our human ancestors, living in Africa millions of years ago, would not have seen the aurora regularly because the auroral oval at that time was farther north. But during periods when the magnetic field was weaker or during particularly strong solar activity, the aurora might have been visible from lower latitudes. Our more recent ancestors, the humans who migrated northward into the Arctic regions over the past tens of thousands of years, would have seen the aurora regularly. The cultures that developed in these northern regions wove the aurora into their mythologies and their understanding of the world. The stories they told about the lights, the spirits dancing, the cosmic battles, the warnings and omens were their way of making meaning of something that was beautiful, mysterious, and utterly beyond their ability to control or fully understand. When we look at the aurora today, with our modern scientific understanding, we know what's causing it. We understand the solar wind and the magnetosphere, the interaction of charged particles with atmospheric atoms. We can predict with reasonable accuracy when auroral displays are likely to be most intense. We have satellite networks that warn us of solar storms and help us anticipate aurora activity. Yet something essential from those ancient perspectives remains. The aurora is still beautiful, still mysterious in its full complexity, still humbling in its grandeur. The physics explains the mechanism, but it doesn't diminish the wonder. The modern aurora hunt. In the modern era, aurora hunting has become a pursuit for both scientists and tourists. Aurora forecasts are available online, provided by space weather prediction centers. These forecasts use real-time data from satellites to predict geomagnetic activity for the next 3 hours, 1 day, and 3 days out. They use the K-index, a scale from 0 to 9 that measures geomagnetic disturbance to indicate the likelihood and intensity of aurora activity. A K-index of 3 or higher typically indicates that aurora is likely to be visible in the auroral oval zone. Higher K indices mean more intense activity over a wider area. Professional aurora photographers have learned to check these forecasts obsessively, watching weather patterns for clear skies and positioning themselves for maximum viewing opportunities. They know the best locations within the auroral zone, the locations with the best views toward the north and the fewest light pollution issues. They have learned through countless hours of observation when the aurora is most likely to be active, typically between midnight and 4 a.m., and they structure their nights accordingly. For tourists, aurora tours have become a major source of income in many northern communities. Tour operators offer a variety of experiences, from simple aurora hunts in heated vans to more exotic options, like viewing the aurora from above in an airplane, or from specialized lodges designed specifically for aurora viewing. Some tourists who are deeply committed to seeing the aurora will spend multiple nights in the north, waiting for the right combination of clear skies and active geomagnetic conditions. Many will return repeatedly, unable to shake the memory of witnessing the lights. The scientific instruments. Modern aurora research relies on a vast network of instruments. On the ground, magnetometers measure fluctuations in Earth's magnetic field, providing real-time data on geomagnetic activity. All-sky cameras are often deployed at aurora research stations, taking photographs continuously or at regular intervals to document auroral displays. Some of these cameras use special filters to isolate specific emission lines, providing data on which atmospheric gases are being excited at particular times. Radar instruments like PFISR, Poker Flat Incoherent Scatter Radar, in Alaska can actually measure the properties of the ionosphere with remarkable precision. They can determine electron density, temperature, and velocity at different altitudes. They can track how these properties change during auroral substorms. They provide information about the actual particles, their density, their energy distribution, their directions of motion. In space, satellites are crucial. Satellites like the Themis spacecraft carry instruments that measure the solar wind, Earth's magnetic field, and energetic particles in the magnetosphere. These measurements help scientists understand what's happening in space before the effects are seen at Earth's surface as the aurora. Some satellites are specifically designed to study the aurora from above, looking down at the brightness of auroral emissions and analyzing their spectral properties. When you combine all these instruments, ground-based and space-based, measuring particles and fields, and light, a rich picture emerges of what's happening during an auroral display. But even with all this technology and data, there are still aspects of the aurora that surprise scientists. There are features of auroral displays that don't fit comfortably into current theories. There are questions about the detailed mechanisms of particle acceleration that remain incompletely answered. The rhythm of the night. Let yourself imagine now that you're sitting outside in the far north on a winter night. The temperature is well below zero, perhaps -20 or -30 degrees Celsius. The stars are brilliant above you, undimmed by atmosphere or light pollution. The Milky Way is clearly visible, a river of light across the dark sky. The air is still and crystalline. The snow reflects whatever light is available, faintly illuminating the landscape with a subtle blue-gray glow. You're not sure if the aurora will appear. The forecast suggested possible activity, but such predictions are far from certain. You wait. Your breath rises before you in clouds of crystalline moisture. Your fingers begin to tingle, despite mittens. Your legs grow cold despite heavy clothes. The night is long, and waiting in the cold tests patience and determination. Then you notice something, a faint glow along the northern horizon. It's barely visible at first, just a subtle brightening, a luminosity that might be mistaken for the last remains of sunset or the glow from a distant city. But you know there are no cities in that direction. You've checked the map. This is the aurora. The glow remains subtle for a long time. 10 minutes pass, then 20. The glow brightens gradually. The outline of an arc becomes visible, a luminous band stretching east-west across the northern sky. It's green, but a soft green, almost ethereal. The arc is not completely uniform. There are slight variations in brightness, slight ripples along its length, the awakening, and then something shifts. The arc brightens. Suddenly, the light intensifies noticeably. The green becomes more vivid, more saturated. The arc that was merely visible becomes striking. The brightness increases to the point where it casts shadows on the snow, thin, indistinct shadows, but shadows nonetheless. The arc begins to move. It ripples. Waves propagate along its length, moving from east to west. The ripples are subtle at first, barely noticeable, but as they develop, they become clear. The aurora is not still. It's in motion, energized, alive with activity. And then the arc breaks up. Bright rays shoot upward from the main arc, pillars of light reaching toward the zenith. These are the auroral rays, the streamers. They're not perfectly vertical, they slant due to the inclination of the magnetic field. They're not perfectly sharp. They shimmer and ripple, but they're unmistakably there. Bright green columns of light reaching toward the stars. More and more rays develop. Soon there are dozens of them, hundreds, stretching across the sky. They don't remain static. They brighten and fade. Some fade completely, only to be replaced by new ones forming from other parts of the arc. Some twist into spiral or helical patterns. Some pulse, growing brighter and dimmer in a regular rhythm that seems almost breathing-like. The scene is utterly silent. There's no sound to the aurora, no crackling or popping or humming. The silence is profound. The only sounds are the sounds of winter itself, the crunch of snow beneath your feet. If you move, the occasional pop of ice expanding in the cold. Perhaps the distant sound of wind. The aurora makes no sound, yet its visual presence is so dramatic that your mind almost expects sound. The disconnection between the visual drama and the silence creates a kind of cognitive dissonance that makes the experience even more surreal, more dreamlike. You stand transfixed. The cold becomes almost irrelevant. Your mind is entirely focused on the sky, on the dance of light unfolding above. Time seems to lose its normal meaning. Minutes pass, and they feel like both seconds and hours simultaneously. You might have been watching for 5 minutes or 50. Your temporal perception has become unreliable. The rays continue their dance. They shimmer and pulse. Occasionally, the entire display brightens dramatically, and for a moment the landscape is illuminated almost as if it were twilight, rather than deep night. Then the brightness fades again, returning to the more subtle glow. But the rays remain bright throughout, persistent pillars of light reaching toward the stars. The peak of the dance. If you're lucky, if conditions are right, and the geomagnetic storm is sufficiently intense, the display reaches a peak. This might come after 10 minutes of increasing activity, or it might take an hour. But when it comes, it's unmistakable. The aurora becomes extraordinarily bright. The green light is so vivid it seems almost artificial, as if someone is projecting it from below the horizon. The rays multiply. Instead of dozens, there might be hundreds, so numerous and so close together that they form an almost continuous curtain of light, rather than distinct individual rays. The curtain ripples and undulates like a curtain caught in a breeze, except this breeze is the magnetosphere, and these movements are driven by the flow of charged particles through Earth's upper atmosphere. And if you're positioned well, and if the brightest part of the display is directly overhead, you might experience the auroral corona. The aurora that has been confined to the northern horizon suddenly seems to surround you. Rays shoot upward in all directions, converging overhead toward a point directly above your head. The effect is spectacular, almost overwhelming. You feel surrounded by light, embedded in a three-dimensional structure of luminosity. The sky is no longer a distant thing you're looking up at. It has become something enveloping, something you're inside of. This moment of peak intensity might last for just a few seconds, or it might sustain for several minutes. But eventually, it passes. The brightness fades. The rays weaken. The display enters a decay phase, the gentle fading. As the display fades, it often becomes even more beautiful in a different way. During the peak, The aurora is dramatic and intense, but as it fades, it often becomes more delicate, more graceful. The green might become softer, more ethereal. The rays might develop a shimmer, a quality of translucence. The colors might become more complex, perhaps hints of purple or red appearing at the edges or at higher altitudes. Some displays fade gradually over many minutes, slowly dimming as the geomagnetic activity subsides. Others fade more quickly, collapsing back to a simple arc or even just a glow within minutes. But as the display fades, it rarely simply becomes dark. Instead, it transitions back to a gentler state, a glowing arc, perhaps a few faint rays, a luminosity on the horizon. The aurora might remain at this gentler level for hours, providing a subtle backdrop to the night sky, or it might fade to nothing, and then, after a quiet period, another display might begin. Auroral activity is often episodic, intense displays alternating with quiet periods. A single night of aurora activity might consist of 3 or 4 distinct substorms, separated by quieter intervals. Each substorm follows a similar pattern: a build-up phase, a peak, and a decay. But the details of each substorm are unique. Each one is a particular creation, distinct from all previous displays and all future displays. The physics behind the beauty. As we rest here, understanding now what we're looking at, we might appreciate the aurora on another level. Every photon of green light you're seeing has been emitted by an oxygen atom in Earth's upper atmosphere. That oxygen atom was struck by an electron or a proton that originated in the solar wind particles that were emitted from the sun and traveled for hours through space to reach Earth. The pattern of the rays tells us about the large-scale structure of Earth's magnetic field. The fact that the rays slant inward toward the magnetic pole reveals the inclination of the field lines at that latitude. The brightness distribution tells us about the intensity and location of the particle precipitation. The colors tell us about the composition of the atmosphere and the energies of the particles. The subtle variations in brightness reveal wave structures in the plasma. The changes from one moment to the next reflect the constantly evolving magnetic conditions in the magnetosphere. The aurora is, in effect, a real-time visualization of the interaction between the sun and Earth. It's nature's way of writing across the sky the invisible forces that are constantly at work around our planet. You're watching fundamental physics, the behavior of charged particles in electromagnetic fields, the interaction of the solar wind with the planetary magnetosphere, the excitation and de-excitation of atomic states made visible and beautiful. Stories written in light. Indigenous peoples of the Arctic, watching displays like the ones you're imagining now, created stories about them. The Inuit tale of spirits playing ball with a walrus head captures something real about the aurora, the sense of game, of play, of movement, without apparent purpose. The warning of the Sami people to not whistle at the lights contains a kernel of something true. The aurora is powerful, even if not dangerous in the literal supernatural sense they imagined. Other cultures created stories that positioned the aurora within their cosmologies, their understanding of how the world worked and what our place in it was. In Japan, before modern scientific understanding, people sometimes interpreted the aurora as a fire-like omen. In Europe, medieval and Renaissance observers often saw the aurora as a sign from God, a celestial omen related to human affairs. When major auroras appeared, they were often recorded in historical documents alongside descriptions of wars, plagues, political upheavals, as if the aurora and worldly events were somehow connected. Modern science explains that the aurora is not an omen in any magical sense. It's a natural phenomenon, driven by natural laws. Yet there's something almost spiritual about standing beneath an aurora display and contemplating it. The sense of connection to something vast, something cosmic, something utterly beyond human control. This is real, even if the mechanisms are now explicable through physics rather than mythology. The diversity of auroral displays. Not all auroras look the same. The displays vary tremendously based on the strength and characteristics of the geomagnetic storm, the local time, the season, and many other factors. A weak aurora might be just a faint glow on the northern horizon, visible only from a dark location and barely noticeable. Such displays go unseen by most people. A moderate aurora displays bright arcs and perhaps some rays or curtains. These are what most people imagine when they think of the northern lights: bright, visible from a considerable distance, obvious and beautiful, but not overwhelmingly intense. A strong aurora becomes a significant event. The display might be visible from cities with significant light pollution. It might be bright enough to illuminate snow-covered ground, enough to cast clear shadows. It might change colors, displaying greens, reds, and purples. To a person experiencing this, it feels like a major event, something worth remembering and telling others about. A very strong aurora, the kind that occurs during the most intense geomagnetic storms, becomes almost overwhelming in its intensity. The aurora might illuminate the landscape nearly as brightly as moonlight, or even brighter. The display might extend far beyond the normal auroral zone, pushing down toward lower latitudes where aurora is normally rare or absent. Such displays are remembered and celebrated. The rarest, most extreme auroras are those that occur during the most intense geomagnetic storms. During the Carrington event of 1859, one of the strongest geomagnetic storms on record, the aurora was visible from the Caribbean. During the May 2024 geomagnetic storm, strong aurora was visible from the southern United States and even from countries near the equator. These events remind us that while the aurora usually occurs in a predictable zone, it can expand dramatically under exceptional circumstances. The colors of extreme displays. We've discussed the normal colors of the aurora, the characteristic green, the rarer red, the subtle blues and purples. But in the most intense displays, the full spectrum of auroral colors can appear. The green and red oxygen lines can appear simultaneously, with their different altitudes creating a layered, rainbow-like effect. The blues and purples from nitrogen can be quite prominent. At the absolute peak of an intense display, the sky can resemble a multicolored aurora, with greens, reds, purples, and even hints of other colors all visible at once. In these extreme cases, the aurora can appear almost surreal. People witnessing such displays often struggle to describe them, because they exceed people's expectations of what the aurora should look like. Some describe them as alien, as if the sky had transformed into something otherworldly. Others describe them as the most beautiful thing they've ever seen. For many aurora watchers, witnessing a really intense display with full spectrum colors is a bucket list item, a peak experience they hope to achieve. The auroral substorm cycle. Scientists studying the magnetosphere have identified a fairly regular pattern to how auroral substorms develop. This is called the auroral substorm cycle. Understanding this cycle helps predict when the aurora is most likely to be active. The substorm cycle begins with a growth phase. During this phase, the solar wind transfers energy to the magnetosphere. The magnetosphere becomes increasingly distorted, stretched out on the night side. Particles begin to accumulate in the inner magnetosphere. There may be a faint auroral arc visible on the ground, but it's not yet bright. The energy is being stored, but not yet released. This growth phase can last from a few minutes to over an hour. During this time, magnetic instruments on the ground show increasing activity, and satellites in space measure increasing particle populations. But to someone watching the sky, the change might be subtle or not immediately obvious. The faint arc that was barely visible might remain barely visible, though perhaps with slightly more structure. Then comes the expansion phase. Something changes. The exact mechanisms are still an active area of research, and suddenly the stored energy is released. Particles that were previously confined are now accelerated to high energies. Bright auroral rays burst upward from the main auroral arc. The brightness of the aurora increases dramatically. The entire auroral oval becomes much more active. This is the most visible phase, the phase that captures the attention of aurora watchers. The expansion phase is when the most spectacular visual phenomena occur. The bright rays, the auroral corona, the multiple colors. This phase typically lasts between 10 and 30 minutes, though it can be shorter or longer. The aurora reaches its peak brightness during this phase and then gradually begins to fade. Finally comes the recovery phase. The brightness decreases, the rays fade. The aurora transitions back to a simpler arc or a glow. The activity level decreases. This phase can last for anywhere from minutes to over an hour. During recovery, the magnetosphere is gradually returning to a more stable configuration, and the particle populations are decreasing. After recovery, the cycle might end if the solar wind activity has decreased sufficiently. But if strong solar wind conditions persist, the cycle might repeat. A new growth phase begins, energy accumulates again, and another expansion phase occurs. A single night of strong aurora activity might consist of 3, 4, or even more complete substorm cycles. The sound that isn't there. One of the enduring mysteries surrounding the aurora is whether it makes sound. For centuries, people living in the Arctic reported hearing sounds associated with the aurora, crackling, popping, rustling sounds that seemed to come from the lights themselves. Some described sounds like burning wood. Others described sounds like snow crunching underfoot, or whispers, or distant singing. Modern science, for most of the 20th century, dismissed these reports. The aurora occurs at altitudes of 100 to 300 kilometers, far too high for sound to propagate down to the ground. The sound waves would simply dissipate in the thin upper atmosphere. Therefore, any sounds reported in association with the aurora must be either imagination or misattribution sounds from the ground being mentally associated with the visual phenomenon. Yet the reports persisted. In recent decades, some scientists have begun to take these reports more seriously. Perhaps, they suggest, there could be mechanisms for very low-frequency sound to propagate down from the magnetosphere to the ground under certain conditions. Perhaps infrasound sound frequencies too low for human hearing might be produced, and could somehow affect human perception in ways not yet understood. The question remains unresolved. Most scientists remain skeptical that the aurora produces audible sound at ground level. Yet the consistent reports from Arctic peoples, particularly from the Sami, cannot be entirely dismissed. It's possible that under certain circumstances, perhaps during particularly intense displays, or at certain locations, some mechanism does produce sound. Or it's possible that humans have a psychological association between visual phenomena and sound, such that looking at the aurora naturally leads to hearing sounds that aren't actually produced by the aurora. This mystery reminds us that even phenomena we think we fully understand can still hold surprises. Even after decades of satellite observations and sophisticated instruments, the aurora can still reveal things we didn't expect. The seasons of aurora. The aurora's visibility and intensity vary with the seasons, though the reasons are subtle. In most locations, the aurora is most visible during the dark season winter at high northern latitudes, or the autumn and spring equinoxes at somewhat lower latitudes. This makes intuitive sense. To see the aurora, you need darkness, and the more darkness, the better. During the polar night of deep winter, in locations above the Arctic Circle, there's darkness 24 hours a day, so the aurora is potentially visible at any time of night. But there's another seasonal variation that's more subtle. Aurora activity, as measured by geomagnetic indices, tends to be stronger during the equinoxes, around March 21 and September 21, than at the solstices around June 21 and December 21. This is called the equinox effect. The reason appears to be related to the tilt of Earth's axis and how this tilt affects the orientation of Earth's magnetic field relative to the solar wind. Additionally, there's a 27-day cycle in aurora activity. This corresponds to the solar rotation period. As the sun rotates, active regions, areas of intense magnetic activity, rotate into and out of view from Earth. When a particularly active region is facing Earth, we tend to experience more solar wind disturbances and stronger geomagnetic storms, leading to more intense aurora. As the sun rotates and that active region rotates away, activity tends to decrease. There's also the 11-year solar cycle. During solar minimum, when sunspots are rare and solar activity is low, aurora occurs but tends to be weaker and less frequent. During solar maximum, when the sun is more active, aurora displays are generally stronger and more common. We are currently approaching a solar maximum, which means aurora watchers can expect a few years of increased aurora activity compared to the past several years. These various cycles daily, 27-day, seasonal and 11-year overlap and interact in complex ways. The aurora's activity on any given night is influenced by all of these factors simultaneously. This is one reason why aurora predictions, while reasonably accurate for the next few hours, become increasingly uncertain further in advance. The technology of aurora hunting. Modern aurora hunters use technology to increase their chances of success. Aurora forecasts and alerts are available from space weather prediction centers. These use real-time satellite data to make short-term forecasts. A hunter checking an aurora forecast website can see the predicted K-index for the next few hours and can make decisions about whether it's worth going out into the cold. Weather forecasts are equally important. An aurora might be occurring, but if the sky is cloudy, you won't see it. Many aurora hunters obsessively check cloud forecasts, looking for the locations where they're most likely to have clear skies on a night when aurora is predicted. In regions near the Arctic where aurora is common, cloudy skies are often the limiting factor, not aurora activity. Cameras have become important tools for aurora observation. Some people take photographs of the aurora using relatively simple equipment: a camera, a tripod, and a wide-angle lens. Others use sophisticated equipment designed to capture the faintest traces of aurora. Aurora photos are often more impressive than what the human eye sees. The camera can accumulate light over several seconds, brightening the display and revealing colors that aren't easily visible by eye. Smartphone apps now exist that predict aurora activity and notify users when conditions are favorable. These apps have made aurora observation more accessible to casual observers who don't want to obsessively check forecasts. Instead, they simply receive a notification when aurora is predicted, and they can decide whether to step outside. All of this technology represents humanity's attempt to increase our connection with this natural phenomenon. The aurora itself is unchanged. It occurs regardless of whether we have forecasts or cameras or apps. But these technologies allow us to encounter the aurora more frequently, to appreciate it more fully, to capture it in forms we can preserve and share with others. The sound of silence under the lights. Let's return now to the scenario of you standing in the Arctic night, watching an aurora display. The aurora has reached its peak, brightened and faded, and now the display is in a quieter phase. The bright rays have largely faded. An arc remains, with perhaps a few subtle rays. The display is still beautiful, but has transitioned to a gentler mode. The profound silence persists. You're aware of how quiet it is. In a landscape covered with snow, far from human civilization, the silence can be almost overwhelming. There's no wind. The air is completely still. There are no animal sounds. Most animals are either hibernating or sleeping. There are no human sounds, no cars, no music, no voices, no machinery. The silence and the visual beauty of the aurora combine to create a particular state of mind. Many people who have experienced this report feeling a profound sense of peace, of calm, of connection to something larger than themselves. This might be a purely psychological reaction to beauty and silence. Or, as some suggest, there might be something more, perhaps the low-frequency electromagnetic fluctuations associated with the aurora, or the infrasound that some claim the aurora produces, might affect human consciousness in ways we don't fully understand. What is clear is that watching the aurora in silence in the cold Arctic night is profoundly different from watching the aurora from a city window or watching aurora footage on a video screen. The full immersion, the involvement of all the senses, the cold air, the sound of your own breathing, the crunch of snow beneath your feet, the sight of the lights, the absence of other human presence creates an experience that photographs and videos cannot fully capture. The dance continues. The aurora display continues. Perhaps there's another substorm. The arc suddenly brightens. New rays form. The display becomes vivid and active again. Perhaps the quiet phase extends for a long time, and you're left watching a gentle glow on the horizon while the stars shine steadily overhead. Time continues to pass. You might check your watch and be surprised to discover that hours have passed since you stepped outside, or you might have no sense of how much time has elapsed. The aurora has a way of distorting time perception, of creating a state somewhat like flow or meditation. The science of the watching experience. As you watch the aurora, your brain is processing an extraordinary amount of information. Your visual system is tracking the movements of the rays, noting the changes in brightness, perceiving the colors and their subtle shifts. Your brain is integrating all of this information into a coherent narrative. There is a display. It is changing. It is beautiful. But more than that, you're in a state of attention that neuroscientists would call flow or absorption. Your normal self-critical thoughts, worries about work, concerns about the future, self-judgments are largely quiet. Your mind is focused on the present moment, on what's happening right now in the sky above you. This state of mind is known to be beneficial for mental health, reducing stress and anxiety. People who meditate regularly or who engage in activities that produce flow states often report greater overall well-being. The aurora, it seems, is not just a beautiful visual phenomenon. It's an experience that can have psychological benefits. In standing beneath it and watching it, you're engaging in something almost meditative. You're allowing the cold Arctic night and the dancing lights to quiet your mind and bring you into the present moment. The memory that remains. Eventually, you will have to go back inside. The cold will become too much, or you'll grow tired, or the display will fade and you'll decide there's no point in waiting in the cold any longer. You'll make your way back to your shelter, back to warmth and light and human civilization. But something of the aurora will remain with you. The experience will linger in your memory, perhaps for days, perhaps for a lifetime. If it was a particularly intense display, you might find yourself frequently recalling it in vivid detail. You might find yourself thinking about how small you felt beneath the lights, how vast the universe is, how connected you are to cosmic processes that occur far above your head and far from any human control. Many people who have witnessed the aurora report that it changed something in them. They feel more connected to nature, more aware of their place in the larger cosmos, more humbled by the grandeur of natural phenomena. Some report that witnessing the aurora gave them a new perspective on their life, helped them prioritize what matters, or inspired them to seek more experiences of beauty and connection to the natural world. The aurora, in other words, is not just something to watch. It's something that touches us, that affects us, that becomes part of our internal landscape of memory and meaning. The next night. If you're still in the north, the next night, you might again venture out to see if the aurora appears. Perhaps the geomagnetic forecast predicts more activity. Perhaps it predicts quiet conditions. If it predicts activity, you'll go out in hopes of seeing another display. If it predicts quiet, you might still go out after all. Forecasts are not perfectly accurate, and unexpected aurora does sometimes occur. The second night's display, if it happens, will be different from the first. Perhaps it will be brighter or fainter. Perhaps the colors will be more vivid or more subtle. Perhaps the display will last longer or be briefer. Perhaps it will have unusual features or will follow a classic pattern. But standing beneath it, even if the display is similar to what you saw the night before, it will feel fresh, new, unique. This is one of the remarkable aspects of natural phenomena. They can repeat, and yet always be different. The ocean waves repeat endlessly, yet no two waves are identical. The sunrise and sunset occur every day, yet each one is particular and unique. The aurora, appearing night after night in the same location, is similarly both repetitive and eternally unique. The science beyond the visible. Everything we've discussed so far about the aurora has focused on what you see, the light, the colors, the movements. But there's an entire science that deals with what you don't see, with the processes happening in the magnetosphere above the aurora. The magnetosphere is a region of space extending thousands of kilometers around Earth, filled with thin plasma gas that has been ionized so that it consists of free electrons and ions rather than neutral atoms. This plasma is threaded by Earth's magnetic field. The solar wind interacts with this magnetosphere in a complex dance. During quiet times, the interaction is relatively gentle. The solar wind flows around Earth's magnetosphere, like water flowing around a stone in a stream. But when solar wind disturbances arrive, especially from coronal mass ejections carrying strong magnetic fields, the interaction becomes more violent. In particular, a phenomenon called magnetic reconnection can occur. Magnetic field lines can snap and reconnect in lower energy configurations, releasing the energy that had been stored in the strained field. This releases energy that accelerates particles to high velocities. These particles, guided by Earth's magnetic field, flow down toward Earth's poles. This acceleration process is one of the most energetic phenomena in the near-Earth space environment. The energy involved is enormous on DES, the order of billions of megawatts during a strong geomagnetic storm. This is comparable to the total energy consumption of human civilization. All this energy is being released in the magnetosphere, with a significant fraction being deposited into the upper atmosphere, where it produces the aurora. The impact on Earth. We've focused so far on the aurora as a visual phenomenon, on its beauty and mystery. But the processes that produce the aurora also affect Earth more broadly. A strong geomagnetic storm can disrupt power grids, damage satellites, and interfere with communications. The most severe storms, such as the Carrington event of 1859, could cause tremendous damage if they occurred in the modern world, where we're so dependent on electrical and electronic systems. Research into the aurora and the associated space weather phenomena is not just scientific curiosity, though that's certainly part of it. It's also important for practical reasons. Understanding and predicting geomagnetic storms is important for protecting our technological infrastructure. At the same time, geomagnetic storms and the aurora remind us that Earth is not an isolated system. We live on a planet that is constantly interacting with the sun, that is influenced by solar activity, that is connected to cosmic processes on scales far larger than any human system. The aurora is a visible manifestation of this connection, a regular reminder that we're part of something vast. The international aurora. We've focused primarily on the aurora borealis, the northern lights. But it's worth remembering that there is also the aurora australis, the southern lights. This is essentially the same phenomenon, occurring in the southern hemisphere. The aurora australis occurs in the same locations at southern latitudes that the aurora borealis occurs at northern latitudes. The aurora australis is most commonly observed from Antarctica, southern Australia, New Zealand, southern Chile, and southern Argentina. The auroras at both poles are driven by the same solar wind disturbances and occur simultaneously. When a geomagnetic storm causes the aurora borealis to dance across the Arctic night, the aurora australis is simultaneously dancing across the Antarctic night. Because the southern aurora has fewer observers, the Antarctic and the far south are less populated than the Arctic and subarctic regions. It's less well known and less frequently documented. But for those who have traveled to see it, the southern lights are equally beautiful. An aurora seen from the top of the world is no more or less wondrous than an aurora seen from the bottom. The future of aurora science. Aurora research continues to evolve. New satellites are being launched with improved instruments for studying the magnetosphere and the particles involved in auroral processes. Ground-based instruments continue to accumulate data. Researchers continue to develop new theories to explain features of auroral displays that don't yet fit comfortably into existing models. One frontier is understanding the small-scale structures within the aurora. Most observations focus on large-scale features, the arcs, the rays, the bands, but there are smaller-scale structures as well. What are the physical mechanisms that produce these fine-scale features? How do they relate to the large-scale processes? These questions are beginning to be addressed. Another frontier is understanding the detailed particle acceleration mechanisms. We know that particles are accelerated to high energies, but the exact mechanisms, the specific processes that do the accelerating, are still an active area of research. Different mechanisms may be dominant under different conditions. Understanding these mechanisms would deepen our overall understanding of the magnetosphere and plasma physics. A third frontier involves understanding the coupling between the magnetosphere and the atmosphere. Energy is being deposited in the 40s, upper atmosphere, during the aurora. But how does this energy affect the atmosphere? Does it influence atmospheric circulation? Does it affect weather? These questions are beginning to be explored. The stories we tell. Throughout history, humans have created stories about the aurora. We've discussed some of the indigenous stories, the Inuit tale of the spirits playing with a walrus head, the Sami warnings about whistling at the lights. Western scientific culture has its own stories about the aurora. The modern scientific narrative about the aurora, the solar wind, the magnetosphere, the charged particles colliding with atmospheric atoms, is a story too. It's a story we tell to explain something that was previously mysterious. It's a story that can be tested, that can be verified through observation and experiment, that continues to evolve as new data becomes available. But it's still a story, an attempt to make sense of a natural phenomenon through language and concepts. What's remarkable is that both the traditional stories and the scientific story can coexist. A person can understand the physics of the aurora, how solar wind particles interact with Earth's magnetic field, how they collide with atmospheric atoms and produce light and still feel awed by the display. Understanding the mechanism doesn't diminish the wonder. If anything, understanding the scale of the processes involved, understanding that you're witnessing the interaction of the Sun and Earth on a planetary scale, understanding that what you're seeing is a real event in which enormous energies are being released, can deepen the sense of awe. The night deepens. As we rest here, as we contemplate the aurora, we might imagine that the night deepens. The display, if one occurred, has faded. The stars shine steadily overhead. The Milky Way arcs across the sky, a river of distant suns. The cold air becomes colder as the night progresses toward its deepest hours, the time just before dawn, when the temperature is usually at its minimum. But even in this quiet period, in the deepest night, the processes continue. Somewhere, solar wind particles are flowing outward from the Sun. Somewhere, they're interacting with Earth's magnetosphere. Somewhere, in the upper atmosphere, excitation and de-excitation of atomic states continues, producing photons of light. The aurora might not be immediately visible, the sky might be clear and quiet, but the processes are happening. In the far north, this might be the time when another auroral substorm begins. The arc that had faded might brighten again. Rays might shoot upward. The aurora might come alive again, as the night reaches what is often its most active time, the hours after midnight. Or the night might remain quiet, with only the stars and the Milky Way visible, with the aurora absent. This, too, is a possibility. Not every night brings an aurora, even in the auroral zone. Sometimes the solar wind is weak. Sometimes the magnetosphere is stable. Sometimes the conditions simply don't align to produce visible auroral activity. The waiting for aurora hunters. There's a particular quality to the waiting. In some sense, waiting for the aurora is similar to waiting for other rare or unpredictable natural phenomena. Waiting for lightning during a thunderstorm. Waiting for the perfect moment of a solar eclipse. Waiting for the sun to set and create dramatic colors. But waiting for the aurora has its own special quality. It's not event-focused in the same way that these other phenomena are. A thunderstorm will eventually happen and will eventually end. A solar eclipse is a specific time. A sunset follows a predictable schedule. But the aurora can appear and disappear somewhat unpredictably. It can be a long wait, or it can be immediate. It can be a fleeting display, or it can last for hours. This unpredictability, combined with the beauty of what you're waiting for, creates a particular psychological state. There's anticipation, obviously, hope that the lights will appear. There's patience, the willingness to wait in cold conditions for hours. There's also a kind of meditative acceptance, recognizing that you're not in control, that the aurora will do what it does, regardless of your desires, and allowing yourself to rest in that lack of control. For many people, this meditative aspect of aurora watching is as important as seeing the lights themselves. The act of standing in the Arctic night, waiting, watching, or being present. This is valuable in itself, independent of whether the aurora appears. The gift of stillness. In our modern world, we are rarely still. We're usually engaged in activity, working, communicating, consuming information, exercising. Even when we're resting, we might be watching screens, listening to music or podcasts, engaging with our devices in some way. Standing in the Arctic night, waiting for the aurora, you're in a state of stillness. Your body might be cold, but your mind can be calm. You're not engaged in activity. You're not consuming information. You're simply present, watching, waiting. This state of stillness, of presence, of not doing, has become increasingly rare in modern life. Yet it may be something we need. Research in neuroscience and psychology increasingly suggests that regular periods of stillness, of meditation, of simply being present, without doing or achieving anything, are beneficial for mental and physical health. The aurora doesn't require you to do anything to appreciate it. You simply have to be there, awake and aware, watching. In a way, this makes the aurora the perfect target for modern meditation practice. The visual beauty provides something for your awareness to rest on, preventing the mind from spinning in its usual loops of worry and self-criticism. The cold and the silence create a sensory environment quite distinct from the warm, noise-filled environments where most of us spend most of our time. The result is an experience of peace and presence that can be deeply restorative. The cycles of existence. The aurora, like so much in nature, reminds us of cycles. On a daily cycle, the aurora is often most active after midnight. On a 27-day cycle, aurora activity waxes and wanes as the sun rotates. On a seasonal cycle, the aurora is most visible during the dark season. On an 11-year cycle, solar activity and aurora activity increase and decrease. On even longer timescales, the magnetosphere has cycled through periods of strength and weakness over millions of years. These cycles nest within each other like Russian dolls, each scale of cycle influencing others. The daily cycle is modulated by the 27-day cycle, which is modulated by the 11-year cycle, which occurs within an even longer context of geological and climatic cycles. As you stand in the Arctic night watching the aurora, you are standing at the intersection of all these cycles. The particular appearance of the aurora on this particular night is the result of all these cycles aligning in a particular way. Change any one of them. Change the time of night. Change the position of the sun's active regions. Change the season, and the aurora would be different. This awareness of cycles within cycles can itself be meditative. It reminds us that we are part of larger patterns, larger rhythms. Our individual lives, our concerns, our worries, our achievements are played out against the backdrop of these vast cycles. This doesn't diminish our individual experiences. Rather, it contextualizes them. It reminds us that we're part of something much larger than ourselves. The colors of emotion. Different people respond to different colors of the aurora. Some say the green aurora fills them with peace and calm. Others find themselves moved more deeply by the red, which appears more rarely and has an otherworldly quality. Still others are most affected by the purple and blue, which can have an almost alien quality. There may be no objective difference in the emotional response that should accompany different colors, yet people consistently report different feelings in response to different auroral colors. Perhaps the rarity of the red and blue aurora means that seeing them feels like a special event, something more significant. Or perhaps there's something in human psychology, something in how we've been conditioned by culture and art, that associates different colors with different emotional states. The green of the aurora has been described as a peaceful green, a calm green, a healing green. It's different from the greens of nature, different from grass or leaves, perhaps because it's luminous, because it comes from within the sky rather than reflecting sunlight. The red of the aurora has been described as mysterious, as ominous, as spiritual. Purple and blue have been described as strange, as otherworldly, as alien. Of course, these are all subjective descriptions. The aurora itself is simply light of particular wavelengths, but the experience of beauty and emotion that accompanies the observation of the aurora is real, regardless of how we interpret it. The silence speaks. We've mentioned the profound silence of watching the aurora in the Arctic night, but silence itself is not simple. There are different kinds of silence. There's the silence created by the absence of sound, the literal acoustic silence of a location far from human civilization, where there are no cars, no machinery, no voices. This is silence, in the most basic sense. But there's also what might be called emotional silence. The silence that comes with stillness, with peace, with the absence of internal chatter. A person standing in the Arctic night might achieve this kind of silence, even though, technically, they might hear their own breathing, the crunch of snow beneath their feet, perhaps the distant wind. The aurora itself contributes to this emotional silence. Its beauty and mystery can quiet the mind in a way that few other experiences can. The usual concerns that occupy our minds, social anxieties, work pressures, self-judgment, fade into the background. What remains is presence, awareness, appreciation, the temperature of wonder. The cold is significant to the aurora experience. Watching the aurora requires being outside, and watching it in the Arctic means being in extreme cold. The temperature might be -20, -30, -40 degrees Celsius, or even colder. The cold is a physical fact. It's uncomfortable. It requires special clothing. It creates real dangers if you stay out too long. The cold demands attention. You must attend to it, must manage it, must respect it. Yet the cold also seems to intensify the experience of watching the aurora. Perhaps it's because the discomfort of the cold keeps you anchored in your body, keeps you present. You can't zone out or drift away when you're cold. Your body constantly brings your attention back to your physical state. Or perhaps the combination of the beautiful, warm-toned colors of the aurora with the cold environment creates a kind of contrast that enhances both. The aurora glows all the warmer against the context of the cold night. The cold air, the crystalline snow, the brilliant stars, all of these serve as a frame that makes the aurora shine all the brighter. There's also something about the willingness to endure the cold that seems to add significance to the experience. You have chosen to stand in a harsh environment, to make yourself uncomfortable, for the sake of witnessing this natural phenomenon. This choice, this commitment, creates a psychological weight to the experience that makes it more memorable, more significant. The gift of simplicity. In our modern world, experience is often mediated. We experience the world through screens. We consume art and music and literature that has been edited and curated and polished. We experience travel through carefully constructed tourist experiences. We rarely encounter raw, unmediated reality. Watching the aurora is different. You're not observing a photograph or a video. You're not experiencing a curated or edited version. You're experiencing the phenomenon itself, directly, as it actually is. There's a simplicity to this. The aurora is what it is. It's not trying to be beautiful, it's simply beautiful as a result of physical processes. It's not trying to communicate a particular message, it's simply an aurora, a natural occurrence. This directness, this simplicity, can be profound. It offers a kind of relief from the constant mediation and curation that characterizes so much of modern life. It's just you, the cold, the night, and the lights in the sky, the vastness above. The aurora occurs at altitudes of 100 to 300 kilometers above Earth's surface. This is far enough that it's beyond the practical reach of any human. You cannot climb or drive or fly to the aurora. It's something that happens above you, something you observe from below. This contributes to a particular quality of the experience, a sense of observing something vast, something that exists on a scale much larger than human. The lights can extend for hundreds of kilometers, stretching across multiple time zones. The processes that produce them operate on scales of thousands of kilometers, involving the entire magnetosphere. When you look up at the aurora, you're looking at something that transcends the human scale. It's not small and intimate. It's not like looking at a painting or a sculpture. It's vast, encompassing, surrounding. This vastness can produce a particular emotional response, sometimes called the sublime. The sublime is distinct from beauty. Beauty is often about harmony and proportion and control. The sublime is about vastness, about being overwhelmed, about recognizing something so much larger than yourself that it humbles you. The aurora, in producing this sense of the sublime, reminds us of our place in Namaste, the larger scheme of things. We are small, we are temporary, we are part of something vast that continues regardless of our individual concerns. The mathematics of light. We've discussed the physics of how the aurora is produced. Solar wind particles colliding with atmospheric atoms, causing them to emit light. But there's also a kind of mathematics to the aurora, a geometry that's worth contemplating. The magnetic field lines that guide charged particles toward the polar regions have a particular geometry. They converge toward the poles, creating a funnel-like structure. The auroral oval, the ring of auroral activity around each pole, has a particular size and shape that can be predicted from Earth's magnetic field geometry and the properties of the solar wind. The individual features of the aurora, the arcs, the rays, the curtains, have their own geometry. The rays are typically aligned with the local magnetic field direction, revealing the shape of the field lines at that location. The arcs mark regions where many particles are being precipitated into the atmosphere. The draperies and curtains reflect waves and instabilities in the plasma environment. In a sense, the aurora is a visualization of invisible mathematical structures. The magnetic field lines cannot be seen, but their presence is revealed by the aurora. The waves and instabilities in the plasma environment cannot be seen directly, but they produce visual patterns in the aurora. The aurora is writing mathematics across the sky in the form of light, the rhythm of expectation. There's a particular rhythm to waiting for the aurora. As the evening progresses toward midnight, as the hours after midnight arrive, anticipation builds. This is the time of greatest likelihood for aurora activity. If it hasn't appeared yet, perhaps it will appear now. Each passing moment could be the moment when the arc brightens, when the display begins. This creates a particular psychological state, a state of anticipation mixed with acceptance. You're hoping for the aurora, but you're also accepting that it might not appear. You're attentive, but not frantically so. You're willing to wait, but not expecting anything. The clock moves toward the time of greatest likelihood. Perhaps you see the first hints of activity, a brightening of the horizon, a faint glow. Your heart rate might increase. This might be it, but it might also be a false alarm, a brief brightening that fades without developing into a true display. Or the night might remain quiet. The hours slide past. The time of greatest likelihood passes. The aurora doesn't appear, but you've been present, you've been watching, you've been part of the process. The absence of the aurora is not a failure. You were here, you watched, you waited. That's enough. The northern journey. Many people feel called to travel north, specifically to see the aurora. There are tours and packages that offer aurora experiences. People book time off work, spend money they've perhaps been saving, and travel to remote locations in the far north to Alaska, Canada, Scandinavia, Iceland, Siberia. This journey north has a quality of pilgrimage about it. People are traveling to see something specific, something they've heard about or imagined, something they feel drawn to. They're making an effort, spending resources, to have this experience. The journey itself becomes part of the experience. The long travel, the journey into unfamiliar territory, the arrival in a place of extremes, all of this contributes to the significance of what's to come. By the time someone arrives in the far north and steps outside to look for the aurora, they're already in a particular psychological state. They're receptive, attentive, open to the experience. For some people, the journey to see the aurora becomes transformative. The experience of travel to a remote location, of confronting the extreme environment, of witnessing natural beauty on this scale, it can shift perspectives, create new insights, inspire changes in how they live their lives. The return to warmth. Eventually, the night ends. Either the aurora display has occurred and faded, or the night has remained quiet. Either way, you will eventually return to shelter, to warmth, to the comforts of human civilization. This transition from the Arctic night back to warmth and shelter is striking. The contrast is dramatic. From the extreme cold of the external environment, you step into a heated space. From the silence and stillness of the night, you enter spaces with sounds and activity. From the vastness and darkness and simplicity of the aurora experience, you return to the complexity and busyness of daily life. The transition can feel jarring. You might find yourself reluctant to come back inside, reluctant to leave the night, reluctant to return to the ordinary world. At the same time, the warmth and comfort feel welcoming. Your cold hands and face warm up. Your tired body relaxes. You begin to thaw, in both literal and metaphorical senses. The fading of the memory. The memory of the aurora begins to fade almost immediately. If you experienced a bright, vivid display, the memory remains relatively clear for a while. But even vivid experiences fade. Details become uncertain. The exact colors become harder to recall. The exact movements of the rays become vague. If you experienced only a faint display, or if you waited and saw nothing, the memory might be even more ephemeral. Did you see that subtle brightening on the horizon? Was it really as beautiful as you remember? Were the colors really that striking? Photography can help preserve the memory. A photograph captures colors and details that human perception might miss or forget. But a photograph also becomes a substitute for the memory. Over time, you might remember the photograph more clearly than you remember the actual experience of standing in the cold and watching the lights. This fading of memory is natural and perhaps even necessary. If all of our experiences remained with crystal clarity indefinitely, we might be overwhelmed. The fading allows us to integrate the experience, to understand what it meant to us, to move forward. Yet there's something poignant about this fading, something that encourages us to be fully present during the experience itself. You can't truly preserve the experience, only the memory of it, which inevitably fades. What remains clear is the feeling of having witnessed something beautiful and vast, the sense of having been touched by something larger than yourself. The calendar of the sky. The aurora is just one of many phenomena that occur in the far northern sky. The night sky at high latitudes offers a succession of phenomena across the seasons and across longer timescales. In the deepest winter, when the polar night reaches its peak, the darkness is absolute and permanent. The stars blaze with extraordinary brightness. The constellations are different from what someone at lower latitudes would see. The familiar constellations of temperate latitudes give way to circumpolar constellations that never set, stars that wheel around the pole all night long. As winter turns to spring, the sun's light begins to return. The period of darkness shortens. The twilight at midday gradually becomes brighter. The stars become less obvious because the sky is no longer completely dark. But now another phenomenon becomes possible. The spring equinox produces not just conditions for aurora, but also a particular quality of light. Summer arrives with the midnight sun. For weeks, the sun never sets. The darkness never returns. At locations far enough north, this can be continuous daylight for weeks or months. The aurora is still occurring. Particles are still being precipitated into the atmosphere. Oxygen and nitrogen atoms are still being excited and emitting light, but the light is invisible, drowned out by daylight. The aurora is always there, even when you can't see it. Then, autumn arrives. The period of daylight shortens. The sun sets once more, and the darkness returns. The autumn equinox brings another period of enhanced aurora activity. Winter approaches again, with its long darkness and its frequent aurora displays. This cycle repeats endlessly. The sky goes through its seasonal patterns. The sun rises and sets or hangs above the horizon, or disappears entirely. The stars turn overhead in their slow wheel. The aurora comes and goes with the seasons and with the solar cycle. The constancy, amid change. One aspect of the aurora that's worth contemplating is its constancy. Humans have observed the aurora for millennia. Ancient peoples created myths about it. Medieval peoples recorded it. Modern people observe it with sophisticated instruments. Throughout all of human history, the aurora has been there, occurring regularly in the far north. Our understanding of the aurora has changed. Our technology for observing it has changed. Our ability to predict it has improved, but the phenomenon itself is fundamentally unchanged. The same physical processes that produced the aurora 1,000 years ago are producing it today. This constancy is comforting in a way. So much changes. Civilizations rise and fall. Landscapes transform. Species go extinct. Technology advances and becomes obsolete. But the aurora persists. It's a reminder that beneath the constant change and flux of human affairs, there are natural rhythms and processes that continue regardless. The aurora, in this sense, is timeless. Not in the sense of being outside of time. The aurora certainly exists in time, occurs in particular moments, changes across seconds and minutes and hours, but timeless in the sense of being ancient, continuous, enduring. The aurora that occurs tonight is connected by an unbroken chain to auroras that occurred thousands of years ago. The humility of understanding. We've discussed the science of the speak, aurora, the solar wind, the magnetosphere, the charged particles, the collision with atmospheric atoms. Modern science can explain all of this. We understand the physics. We can predict when the aurora will likely be visible. We can measure its properties with sophisticated instruments. Yet, understanding the mechanism doesn't eliminate the sense of mystery. In some ways, it deepens it. The more we understand about how the aurora works, the more we understand how vast and complex the processes involved are. The more we understand about the magnetosphere, the more we realize how much remains unknown. The more precisely we can measure auroral properties, the more we discover patterns and features that don't fit comfortably into existing theories. Science provides knowledge, but not omniscience. It provides explanations, but not complete explanations. Science strips away some mysteries, only to reveal deeper mysteries beneath. This is the way of all scientific understanding. It expands our knowledge, while simultaneously revealing the limits of our knowledge. The aurora reminds us of this beautifully. We understand a lot about it, yet it remains mysterious, complex, incompletely understood. The science doesn't diminish the wonder. If anything, it enhances it by revealing the depth of what's happening. The gift of darkness. In our modern world, darkness has become something we avoid. We illuminate our cities. We light our homes. We carry lights with us in the form of screens and flashlights. We rarely experience true darkness. The far north, especially during the winter, offers true darkness. The kind of darkness that existed before electric light, before civilization as we know it. This darkness is not frightening, or at least, the fear of it fades quickly when you realize there's nothing to fear. The darkness is simply darkness, the absence of light. This darkness is a gift, in a way. In a world where light and information and stimulation are constantly available, The darkness of the Arctic night offers relief. It offers a return to a more primal condition, a condition in which humans lived for most of our evolutionary history. The darkness makes the stars brilliant. The darkness makes the aurora visible. The darkness, in its simplicity and vastness, offers a kind of peace. The end of winter, the beginning of springtime, moves differently in the far north. In deep winter, the days are either non-existent during the polar night or extremely short at slightly lower latitudes. Each day is darker than the day before. The cold deepens. The environment becomes more extreme. But eventually, winter reaches its turning point. The shortest day passes the winter solstice, and from that moment on, the days begin to lengthen. The sun's daily arc begins to rise higher. The darkness begins to retreat. This turning point has significance that goes beyond the physical calendar. Psychologically and spiritually, the winter solstice and the gradual lengthening of days that follows mark a turning point. The worst of winter is past. Spring is coming. The aurora continues through this period. It remains a companion through the long darkness. And as spring approaches and the darkness shortens, the aurora becomes more difficult to see, not because it's not occurring, but because the sky is no longer dark enough for it to be visible. By the time true spring arrives and the sun begins to remain above the horizon for extended periods, the aurora is hidden by daylight. The long winter's companion fades from view, waiting for the return of autumn and the return of the long darkness. A state of readiness. For those who live in the aurora zone, or who travel there to see it, there develops a kind of perpetual readiness. On clear nights during the season of darkness, there's always a possibility that the aurora will appear. This creates a state of readiness, a willingness to step outside at any time, to look upward, to check the night sky. This readiness might seem exhausting, but many who experience it report that it's actually restorative. It keeps you connected to the natural world. It makes you pay attention to the night sky, to the stars, to the weather, to the subtle signs that might indicate auroral activity. It creates a kind of vigilance that's different from the stressed vigilance of modern life. This is a relaxed, open vigilance, a willingness to be surprised by the natural world. The global indigenous witness. Before science gave us spectrographs and satellites, before we could measure the solar wind or analyze spectral lines, indigenous peoples of the Arctic bore witness to the aurora. They didn't understand the mechanism, but they understood the phenomenon intimately. They lived with it, watched it regularly, incorporated it into their understanding of the world. The Inuit peoples Inupiat, Yupik, Kalalit, and others developed narratives about the aurora that reflected both the beauty they observed and the environment in which they lived. The harsh Arctic landscape, the long darkness, the dependence on careful observation of the night sky for navigation and prediction, all of this shaped how they understood the lights. The image of spirits playing with a walrus head is vivid and specific. It captures something real, the sense of play, of entertainment, of purposeless motion. The aurora seems to move as if engaged in a game, as if driven by something other than mere physics. Of course, the game is driven by physics, the interaction of the solar wind with the magnetosphere. But the metaphor is apt. There is a playfulness to the aurora, a quality of motion without obvious purpose, a quality that invites observers to interpret it as play. Other indigenous interpretations emphasized danger. Some of the Sami traditions warned against the aurora, suggesting that it was not to be trifled with. This too reflects something true. The aurora is a manifestation of enormous energies, of processes on a planetary and solar scale. While the aurora itself poses no danger to people on the ground, the underlying processes are indeed energetic and violent on their scale. These traditional interpretations were not primitive or incorrect. They were sophisticated ways of encoding knowledge. The Inuit and Sami peoples knew when the aurora was likely to appear. They recognized different types of auroral displays. They understood that the aurora correlated with other phenomena, with weather, perhaps, or with animal migration patterns, or with the seasonal cycle. Their narratives encoded this knowledge in a form that could be transmitted orally across generations. Modern science hasn't made these traditional understandings obsolete. Rather, science has expanded and deepened them. We now understand that the aurora is indeed related to cycles: the 11-year solar cycle, the 27-day rotation of the sun, seasonal cycles, daily cycles. We understand that auroral activity does affect the upper atmosphere in ways that might influence weather, though the effects are subtle. We understand the mechanisms in detail, while still appreciating the wisdom embedded in traditional narratives. The European medieval understanding. When European observers became aware of the aurora, particularly as exploration and colonization brought Europeans to higher northern latitudes, they interpreted it through the frameworks available to them. In the medieval period, the aurora was often seen as a celestial omen, a sign from God or the heavens regarding earthly affairs. Chronicles from medieval and Renaissance Europe occasionally record auroras, often in association with significant events. A particularly bright aurora might be recorded alongside descriptions of war, plague, political upheaval, or the death of a monarch. This reflected a worldview in which the celestial and terrestrial realms were believed to be connected, in which heavenly signs communicated meaning about earthly events. We can recognize this as a kind of error. The aurora doesn't actually predict or control earthly events. Yet it also reflects an important intuition. The heavens and earth are indeed connected. We now understand this connection in terms of magnetospheric physics rather than divine communication. But the fundamental insight that events in space affect Earth, that we're not isolated, remains valid. The scientific illumination, the scientific understanding of the aurora, developed gradually through the 18th and 19th centuries, as researchers became more systematic in their observations, and as the science of electricity and magnetism advanced. By the early 20th century, scientists had developed a fairly complete picture of how the aurora was produced. The key breakthrough came in the space age, when satellites could directly measure the solar wind and the magnetosphere. Suddenly, the theoretical predictions could be tested against actual measurements. The puzzles that had remained intractable on the ground could be solved by observations from space. One of the great realizations of space-age aurora research was the complexity of the magnetosphere. The magnetosphere is not a passive shield, simply blocking the solar wind. It's a dynamic system, constantly evolving, constantly responding to changes in the solar wind, constantly exchanging energy and particles with both the solar wind and Earth's atmosphere. Understanding this has practical implications. Geomagnetic storms, driven by solar activity, can disrupt power grids and damage satellites. Modern space weather forecasting, which allows us to predict when such storms are likely and prepare our technology accordingly, exists because of decades of research into the aurora and the magnetosphere. But understanding also has spiritual or philosophical implications. It reminds us that Earth is not isolated, that we live in a system, that external forces, the sun, the solar wind, the magnetosphere constantly influence our world. We're part of something vast and interconnected. The modern aurora experience. In the modern era, aurora watching has become simultaneously more accessible and more mediated. More accessible because information about when and where to see the aurora is readily available online. More mediated because we can experience the aurora through photographs, videos, and internet streams before or instead of witnessing it in person. For the professional aurora photographer, the experience involves checking forecasts, analyzing weather patterns, positioning equipment, waiting in the cold, and attempting to capture the lights in images. The photographs can be stunning, revealing colors and details that the human eye might miss. But the photographs are also a substitute for the direct experience. For the tourist joining an aurora tour, the experience is more curated. The tour company handles the logistics, provides some level of comfort, heated tours, perhaps hot drinks, and guides the tourist through the process. The experience is less spontaneous, less dependent on personal knowledge and preparation, but more accessible. For the local living in the Aurora zone, the experience is woven into daily life. The aurora is something that happens regularly, something that doesn't require special planning or travel. There's a casual familiarity to it, yet even locals who have seen the aurora hundreds of times report that it never becomes boring. Each of these modes of experiencing the aurora is valid. Each provides something different. The photograph preserves a moment. The guided tour provides education and social connection. The direct experience provides immediacy and personal encounter. The colors across cultures. Different cultures have responded to the different colors of the aurora in different ways. The dominant green color has been interpreted as peaceful or healing in many traditions. The rarer red has often been interpreted as more ominous or mysterious. In some traditions, the red aurora was seen as particularly significant. The Japanese term for the aurora is Kitagatakaze no Kukai Mono, or more commonly, Kitakazekaze no Kukai Kukai, reflecting both the northern location and the cosmic significance. Yet some Japanese folklore emphasized the red color, interpreting red auroras as particularly important or ominous. In Scandinavian and other European traditions, the colors of the aurora sometimes were interpreted through the symbolism of fire. The aurora glowing red was seen as fire from the sky, a portent or a sign. This reflected the visual similarity between the red aurora and fire, yet also captured something about the dynamic nature of the aurora, its activity and energy. In Polynesian traditions, the aurora was less frequently observed but occasionally documented in historical records, particularly during periods of unusual solar activity that pushed the auroral oval to lower latitudes than usual. When the aurora was visible from Polynesian locations, it was incorporated into navigation stories and mythologies. The universal aspect of auroral interpretation across cultures is that it's taken seriously. Regardless of how different cultures interpret the aurora, they recognize it as significant. It's not treated as a casual or ordinary phenomenon. It's incorporated into cosmology, into spiritual understanding, into the cultural narrative of meaning, the physics of magnetospheric storms. To deeply understand the aurora, we must understand the processes that drive it. The solar wind flowing from the sun is not uniform. It varies in density, in velocity, in temperature, and in magnetic field strength. When a coronal mass ejection, CME, erupts from the sun, it can send billions of tons of plasma rushing toward Earth at speeds up to thousands of kilometers per second. When this disturbance arrives at Earth's magnetosphere, the magnetosphere responds. The magnetic field is compressed on the sun-facing side. The tail of the magnetosphere on the night side becomes elongated and distorted. This configuration is unstable, full of stored energy. The instability is eventually relieved through processes like magnetic reconnection. When magnetic field lines reconnect into a lower energy configuration, the energy that had been stored is released. Particles accelerate to high speeds. These particles are guided by the magnetic field lines toward the polar regions. This process is remarkably efficient, at converting the energy of the solar wind into energetic particles that can reach the upper atmosphere and produce the aurora. If the disturbance is particularly strong, producing intense auroras, it means that an enormous amount of energy is being released and directed toward the upper atmosphere. The upper atmosphere responds to this input of energy. The particles deposit their energy through collisions with atmospheric atoms and molecules. The atmosphere heats, winds develop. The structure of the upper atmosphere is disturbed. Interestingly, one of the ways this energy is dissipated or converted to other forms is through the aurora itself. The light emitted by the aurora represents energy that has been converted from the kinetic energy of particles into photons. So the aurora is quite literally a way that the upper atmosphere is disposing of the energy delivered by the solar wind and magnetosphere. This energy processing is continuous. On any given night, even during quiet geomagnetic conditions, the aurora is occurring. Energy is being dissipated. The system is functioning. During disturbed conditions, the energy dissipation accelerates. More power is being handled through the aurora. The aurora brightens. The transformation of observers. Many people report that witnessing a bright aurora in person is a transformative experience, not in the sense that it produces dramatic personality changes or radical shifts in life trajectory, though it can sometimes do that. Rather, it's transformative in the sense that it shifts perspective, that it provides a new lens through which to view the world and one's place in it. People often report feeling simultaneously smaller and larger after witnessing the aurora. Smaller, because confronting the vastness of the cosmos, the power of natural phenomena beyond human control, can humble us. Larger, because the experience of being connected to cosmic processes, of witnessing something so vast and beautiful, can expand our sense of self and possibility. Some report that witnessing the aurora clarifies priorities. The concerns and worries that normally occupy their minds, social anxieties, career pressures, financial concerns seem smaller, less pressing, in the context of the vast cosmos. What matters becomes clearer. Others report that witnessing the aurora deepens their sense of connection to the natural world. Having stood beneath the aurora, having felt its presence, they feel more connected to nature more broadly. They pay more attention to the sky, to weather, to seasonal changes, to the patterns of nature. Some report spiritual or mystical experiences in connection with viewing the aurora. They feel themselves connected to something larger, something sacred perhaps, something that transcends ordinary understanding. Whether this reflects something objectively true about the aurora or is a subjective interpretation that observers bring to it, remains an open question. From a scientific standpoint, we can't verify the existence of spiritual or transcendent qualities, yet we can acknowledge that people have these experiences, and that these experiences are meaningful to them. The poetry of magnetism. As we contemplate the aurora and its deep workings, we might reflect on the poetry of magnetism itself. Magnetic fields are invisible, yet they structure the behavior of charged particles in profound ways. They're invisible, yet their effects are everywhere in the operation of electric motors, in the functioning of compasses, in the behavior of the solar wind and magnetosphere. The aurora, in a sense, makes the magnetic field visible. The magnetic field lines themselves are invisible, but the particles moving along them are guided, and when those particles collide with atmospheric atoms, light is produced. The light traces the magnetic field lines. The aurora is the magnetic field rendered visible. In this way, the aurora is a beautiful example of how invisible forces structure visible phenomena. We live in a world full of such invisible structures: electromagnetic fields, gravitational fields, quantum fields, underlying subatomic particles. These invisible structures determine how the visible world behaves. The aurora is a reminder of this. There's something poetic about a phenomenon that makes the invisible visible, that renders structure and force as light and color. The poetry lies not in any meaning the aurora carries, but in its nature, the way it transforms the abstract into the tangible, the theoretical into the visible. The Night Sky Archive. Imagine for a moment that you're an astronomer, a researcher whose work involves understanding Earth's space environment. You spend your nights looking at data from satellites, at measurements from ground-based instruments, at photographs and videos of auroras captured by observers around the world. You're adding to an archive of knowledge, a vast collection of observations spanning decades. This archive is not merely a collection of data points. It's a historical record, a chronicle of how the aurora has behaved, how the sun has behaved, how the magnetosphere has responded. From this archive, patterns emerge. We can identify the 11-year solar cycle in the archive. We can identify seasonal variations. We can identify the long-term trends in solar activity. But more than that, the archive contains surprises. There are auroras that don't fit the expected patterns, that display unusual features, that challenge our understanding. These surprises drive further research. They push the boundaries of our knowledge. They remind us that despite our sophisticated instruments and our accumulated data, the aurora still holds mysteries. For someone who studies the aurora, spending years accumulating observations and understanding patterns, there's a particular form of knowledge that develops. It's not just intellectual knowledge of the physics. It's a kind of intuitive knowledge, developed through looking at hundreds or thousands of auroras, of what a normal aurora looks like, what patterns are common, what features are unusual. An experienced aurora researcher can sometimes look at a single photograph and immediately recognize something unusual about it, can see patterns that would take a less experienced observer much longer to identify. This is the kind of knowledge that comes from deep engagement, from spending time with a phenomenon, from developing a relationship with it. The waiting and watching stations around the world. There are locations dedicated to aurora observation and research. Some are major research stations maintained by universities or government agencies. Others are more modest, perhaps amateur observers maintaining instruments in remote locations. In Tromsø, Norway, there's a planetary science institute with equipment dedicated to studying the aurora. In Fairbanks, Alaska, the University of Alaska maintains extensive auroral observation equipment. In Sodankylä, Finland, there's a geophysical observatory with decades of continuous measurement. In the Canadian North, in Siberia, in Antarctica, there are more stations, each contributing to our understanding. These stations are not just places where data is collected, they're also places where observers gather, where people watch together, where the aurora is discussed and appreciated. There's a culture at these stations, a sense of shared commitment to understanding a phenomenon. Some of these stations have been operating for decades, some for generations. The observations made in the early 20th century laid groundwork for later research. Scientists who worked at these stations in the 1,960 seconds and 1,970 seconds trained the next generation who used satellites to measure what previous generations could only observe from the ground. There's something moving about the idea of this continuity. Scientists across the globe, across generations, all focused on the same phenomenon, all contributing to the slow accumulation of understanding. The aurora has been witnessed by countless eyes, measured by countless instruments, studied in countless hours of work. Yet it remains essentially itself, occurring night after night in the far north, beautiful and complex regardless of whether anyone is watching or studying it. The colors we cannot see. We've discussed the colors visible to the human eye, the green, the red, the purple and blue. But the aurora emits light across a broader spectrum than we can perceive. There's ultraviolet light emitted during intense displays. There's infrared light. There are X-rays and other high-energy radiations. Satellites equipped with ultraviolet sensors have observed auroras that appear dramatically different when viewed in ultraviolet light compared to visible light. Instruments that detect infrared radiation reveal the thermal signatures of the aurora, showing the heating of the upper atmosphere. X-ray observations reveal high-energy processes occurring during the most intense geomagnetic storms. This is a reminder that our sensory perception, while wonderful and sufficient for navigating daily life, provides only a narrow window into the full spectrum of reality. The visible aurora is beautiful, but it's only a fraction of what's actually happening. The full aurora, if we could perceive all wavelengths simultaneously, would be far more complex and intricate than what our eyes reveal to us. In a metaphorical sense, this is true of much of reality. We perceive a narrow slice of what's actually there. Much remains invisible to us, perceptible only through instruments that extend our senses. The aurora seen in visible light is like the visible region of an iceberg, while invisible to us but still very much real. The solitude of the observer. For the person who steps outside into the Arctic night to watch the aurora, there's often a profound solitude. Even if there are other people nearby, even if you're part of a tour group, there's a sense of individual encounter with the phenomenon. Each person watching the aurora is alone with it, regardless of other watchers. This solitude can be uncomfortable for some. The cold, the darkness, the vast, empty landscape, the presence of something so vast and powerful and indifferent to human concerns for some people. This combination produces a kind of existential unease. For others, the solitude is deeply welcome. In a world where we're almost constantly connected to other people through technology, where we're almost never truly alone, the experience of standing alone in the Arctic night beneath the aurora offers a particular kind of relief. It's a return to solitude, not as isolation, but as a natural condition, a way of being that humans evolved with, and that modern life has largely eliminated. The aurora witnessed in solitude has a quality different from the aurora witnessed in a group. In a group, there's communication, shared experience, collective response. In solitude, the experience is entirely internal. You're alone with the lights, alone with your thoughts, alone with the vast cosmos above. The rhythm of preparation. For those who travel north specifically to see the aurora, there's a particular rhythm to the experience. First comes the planning phase, researching locations, booking travel, preparing equipment, checking forecasts. This phase can extend over weeks or months. Then comes the arrival in the north. There's adjustment to the new environment, the extreme cold, the darkness, or the unending daylight if you arrive in summer. The landscape so different from what most people are familiar with. The arrival phase might last a day or a few days. Then comes the watching phase. If you've planned a multi-day aurora trip, you might spend several days or weeks watching the night sky. You fall into a rhythm of sleeping during the day, staying awake at night, checking forecasts, going outside to watch, waiting, watching, perhaps seeing the aurora, perhaps not. For those who see the aurora during this time, there's the phase of experiencing it, which we've discussed extensively. For those who don't see it despite the wait, there's the phase of acceptance, coming to terms with the possibility that this particular trip won't result in witnessing the lights, yet having done the trying, having made the effort. Then comes the departure phase. You leave the north and return to your normal life, carrying with you the memory of the experience or the memory of the attempt. The rhythm is different for locals. They don't arrive and depart. They live in a state of perpetual readiness during the season of darkness, in a state of perpetual absence of the aurora during the season of light. The northern sky all night. In locations above the Arctic Circle during the winter, the sun doesn't rise. The sky is dark for 24 hours a day. This produces a particular psychological effect. The constant darkness can be disorienting, can affect mood, can require adjustment. Yet this continuous darkness also offers unique opportunities. The sky is always dark. Observations can be made at any time. If the aurora is active, it's potentially visible at any hour. For aurora researchers, this is ideal. For tourists, it can be slightly disorienting. There's no clear day-night rhythm, just constant night. At slightly lower latitudes, the situation is different. The sun doesn't rise, but it circles the horizon, never fully setting, never fully rising. The sky is twilight during the supposed daylight hours, dark during the supposed nighttime hours. This produces a world of constant twilight, beautiful but also somewhat dreamlike. Further south, the seasons change more gradually. In places at around 60 degrees north, southern Alaska, southern Canada, southern Scandinavia, the winter still brings long darkness, but not continuous darkness. In midwinter, the sun might be above the horizon for only a few hours at midday, but there is still a day-night cycle, just compressed. These different latitudes produce different experiences. The far north offers the deepest darkness and the most continuous aurora season. The lower latitudes offer a more familiar day-night cycle, but a more limited aurora season. The journey south. As we move away from the Arctic regions toward lower latitudes, the aurora becomes rarer. A person living in Seattle or Boston or London might go their entire life without seeing the aurora. Or they might see it once, during a particularly strong geomagnetic storm, and have that one memory forever. The rarity increases the specialness. A person living in Fairbanks might see the aurora dozens of times per year and yet still find it beautiful. But a person living in Boston who sees the aurora once in their life experiences it as a remarkable event, something to remember and recount. There's a trade-off. The Arctic observers have frequency and familiarity, but perhaps less of the sense of special occasion. The distant observers have rarity and intensity of experience, but they might miss the depth of understanding that comes from regular observation. For some people, this distance makes the aurora more desirable. It becomes something to pursue, something to travel for, something that doesn't come to them but that they must actively seek. The pursuit becomes part of the experience. The historical records, before modern instruments and satellites, the only record of aurora activity came from human observations. Chronicles, manuscripts, historical records from various cultures documented auroras, particularly the bright ones, the ones that were impossible to miss. Chinese astronomers kept meticulous records. European chroniclers documented auroras. Scholars have analyzed these historical records to understand long-term patterns of solar activity. The records show periods of high aurora activity and periods of lower activity, matching what we understand about solar cycles. The historical records also show exceptions and anomalies. There are accounts of auroras so bright they were visible in daylight, auroras with unusual colors, auroras that produced audible sounds according to the accounts. Some of these exceptional records correspond to times of unusual solar activity that we can now verify through other means. These historical records remind us that the aurora is not a modern discovery. Humans have been observing it for thousands of years. Our modern scientific understanding has added explanatory depth, but the phenomenon itself is ancient, as old as Earth's magnetic field and atmosphere. The dance continues through time. As you rest here now, contemplating the aurora, understand that it's dancing above the Arctic, whether you're watching or not. At this very moment, in the far north, the dance continues. The aurora occurs with or without observers. It occurs in locations where no humans are present, where no instruments are measuring it, where the display happens in complete solitude in the vast Arctic wilderness. This is perhaps one of the most profound aspects of the aurora. It's not a phenomenon that requires an observer to be complete. It occurs whether witnessed or not. The beauty of it continues, whether anyone sees it or not. The majesty of it remains whether anyone is present to appreciate it. This is true of all natural phenomena. Of course, the mountains are beautiful whether anyone sees them. The ocean waves continue to crash, whether anyone watches. The stars shine, regardless of observation. But we often need the reminder that the world is not created for human observation, that beauty and meaning exist independent of human awareness. The aurora provides this reminder powerfully. It's something that happens in a place most humans will never visit. At times most humans will never witness, with a kind of indifference to human concerns or desires. It simply occurs as part of the natural processes of the cosmos. The invitation. If you have ever felt called toward the north, toward the aurora, toward the experience of standing beneath the lights, that call is valid. That desire to witness something beautiful and vast, to travel to a place of extremes, to encounter the natural world directly, these are legitimate desires. The journey to see the aurora is not necessary for a full or meaningful life. Many people never see it and live deeply satisfying lives. But for some people, the pull toward the aurora is real. For some, the thought of standing in the Arctic night beneath the dancing lights calls to something deep within them. If you feel this call, if the story of the aurora speaks to you, if you find yourself wishing you could witness it in person, then perhaps one day you will make the journey north. Perhaps one day you'll find yourself in the cold darkness, looking upward, waiting, watching, or perhaps not. Perhaps you'll rest here, imagining it, and that imagination will be enough. Perhaps the contemplation of the aurora, the understanding of its nature and beauty, will be your encounter with it. There's no right way to relate to the aurora. The person who travels to the Arctic, spends money, endures hardship, and stands in the cold for hours, watching the lights they're having, one valid kind of experience. The person who reads about the aurora, watches videos of it, contemplates it from a warm room there, having a different but equally valid experience. The person who never thinks about the aurora at all their life is complete without it. The aurora exists for those who look for it, and for those who don't. It dances in the far north, indifferent to human attention or lack thereof. It has danced for millions of years. It will continue to dance for millions more. In its way, this constancy, this indifference, this persistence, this is a kind of comfort. The aurora reminds us that the cosmos continues regardless of our individual desires or experiences. We're part of something larger, something that will go on after we're gone. The breathing of the night. In the Arctic night, watching the aurora, you might become aware of your own breathing. The cold makes your breath visible. It clouds before you in crystalline patterns. Your breathing becomes audible in the profound silence. You become aware of your body, your heartbeat, your vital processes, in a way that daily life often obscures. This awareness of your own breathing and heartbeat in the context of witnessing the aurora creates a particular connection. Your body, with its rhythms and processes, is responding to the environment. The aurora, with its rhythms and processes, is dancing overhead. You're part of your own biological processes, and part of the larger cosmic processes represented by the aurora. There's something grounding about this awareness. It brings you fully into the present moment. fully into embodied experience. You're not thinking about your worries or your future plans. You're simply present, breathing, standing, watching. The science of presence. Modern neuroscience reveals something interesting about what happens in our brains when we're fully present, when we're engaged in what researchers call flow or absorption. During these states, certain regions of the brain show reduced activity, specifically regions associated with self-referential thinking and rumination. At the same time, regions associated with attention and sensory processing show heightened activity. In practical terms, this means that when you're fully engaged in watching something beautiful like the aurora, your brain is in a state that's beneficial for you. Stress hormones decrease. Regions associated with anxiety show reduced activity. The constant internal chatter about past and future quiets. The aurora, in this sense, is not just beautiful and interesting intellectually, it's also therapeutic. Standing beneath it, watching it, allowing yourself to be fully present to the experience, your brain enters a state that reduces stress and promotes well-being. This is one reason why people who have witnessed the aurora often report feeling rejuvenated by the experience, as if a burden had been lifted from them. The beauty of the aurora, combined with the meditative state induced by being present to that beauty, creates a healing effect. The questions that remain, for all the progress that science has made in understanding the aurora, questions remain. How exactly does particle acceleration occur in the magnetosphere? What determines the precise shape of auroral features? How does the upper atmosphere respond to auroral energy input in the long term? These and many other questions continue to drive aurora research. The questions are not failures of science. Rather, they represent the frontier of knowledge, the places where our understanding is incomplete. Each question answered leads to new questions. This is the nature of scientific understanding. It expands and deepens, but it never reaches a point of complete closure. In a way, this incompleteness is comforting. It means that there's always more to discover, always new surprises waiting. The aurora will never be completely understood in the sense of having no mysteries left. There will always be something new to learn about it. The descent into sleep. As we approach the end of our journey together, the story draws toward its close. You've traveled with us through the science of the aurora, through the experience of witnessing it, through the cultural and personal meanings it carries. You've contemplated its beauty and mystery, its connections to the cosmos and to ourselves. Now, as this story concludes, allow yourself to sink deeper into rest. The aurora continues its dance in the far north, but you can rest here, in the comfort of warmth and safety, carrying the aurora with you in thought and imagination. Your breathing has perhaps slowed. Your body has relaxed. Your mind, having journeyed through so many contemplations, is ready for rest. The story has carried you where it needed to go. The final gift. The aurora offers us a final gift as we rest. The gift of reminder. It reminds us that beauty exists independent of human perception. It reminds us that we're part of something vast. It reminds us that the cosmos is dynamic, active, constantly in motion. It reminds us that processes on unimaginable scales are constantly occurring around us. It reminds us that we live in connection with the sun, with the solar wind, with the magnetosphere, with forces that span from the microscopic to the planetary. The aurora reminds us to look up, to pay attention to the sky, to wonder. In a world where we spend so much time looking down at screens, the aurora calls us to look up. In a world where we're often isolated indoors, the aurora calls us to step outside. In a world where our time is fragmented into small tasks and goals, the aurora calls us to be still, to wait, to simply be present. The eternal lights. As you drift now towards sleep, Imagine yourself beneath the northern lights one final time. The aurora dances overhead, green and red and purple, rippling and shifting. The silence is profound. The cold is sharp but not unbearable. The stars shine steadily above the aurora. You're standing in a place of extremes, witnessing a phenomenon that has occurred for billions of years, that will continue for billions more. Countless humans have stood in similar locations and witnessed similar lights. Countless humans will stand in similar locations in the future and witness similar lights. You're part of a chain of observers stretching backward in time and forward into the future. But for now, in this moment, the aurora is yours alone. The lights dance for you, above you, eternal and beautiful, and utterly indifferent to whether you're watching or not. And as you watch, feeling the cold, hearing the silence, seeing the lights, your mind begins to quiet. The aurora does its work of meditation, of bringing you fully into the present moment. Your thoughts slow, your concerns fade. You're simply here, simply present, simply witnessing. The aurora continues its dance. It will continue tonight, will continue tomorrow night, will continue next week and next year. It will continue after you've returned to your normal life, after the memory of it has faded somewhat, after it recedes into the past. It will continue whether you ever see it in person or only in imagination. The blessing of the night. Let the aurora bless you with its presence, whether you see it in reality or in imagination. Let it remind you of the vastness of the cosmos, the beauty of natural phenomena, the constancy of processes much larger than yourself. Let the memory of the aurora, or the imagined experience of it, rest with you as you sleep. Let the night sky, in all its mystery and beauty, carry you toward rest and dreams. The aurora dances on. In the far north, in the deep cold, in the profound darkness, the lights continue their ancient dance. They dance above sleeping animals, above empty tundra, above small human settlements. They dance whether anyone watches or not. And you, dear listener, can rest now. The story of the aurora has been told. The journey has reached its destination. Let yourself drift now, gently and peacefully, into sleep. Close your eyes. Let the image of the dancing lights rest behind your eyelids. Feel the calm that comes from contemplation and presence. Allow your body to relax completely. Your mind is tired from traveling so far, from contemplating so deeply. It's time to rest. The northern lights continue their dance in the far north. And here, in this warm and safe place, you can rest, carrying the memory and imagination of those distant lights with you into dreams. Sleep now, dear listener. Sleep beneath the northern lights, whether real or imagined. Sleep peacefully, knowing that the cosmos continues, the aurora dances, and all is well. Good night. May your sleep be deep and restful. May you wake refreshed, carrying with you the memory of the aurora and all the contemplations that journeyed with it. The northern lights keep watch through the night, and now, so do your dreams.